Hey everybody, it's Mr. Mott. What I want to do is give you an introduction into thermodynamics, which involves energy transfer in chemical reactions. The first law of thermodynamics says that energy cannot be created or destroyed, it's just changing form. And what we need to think about and keep in mind for this unit is the system and the surroundings. The system is typically your chemical reactions, the surroundings might be the air, might be the cup or beaker that the reaction is taking place in. When we say that the system is acting on the surroundings, we assign it a negative sign. So in science, we know that the sign convention is really important. So if the system is acting on the surroundings, it's a negative sign. What could be acting on the surroundings? Well, typically it's going to be heat. It can involve work as well. Work in the perspective of chemistry has to do with a change in moles of gases. If the surroundings are doing work onto the system, we assign that a positive sign, and that too would involve either heat and or work. All right. One of the formulas that your book gives you has to do with the enthalpy of a reaction, which is the symbol is delta H. So delta H is the enthalpy, which is a fancy way of saying the heat involved in a chemical reaction. And the enthalpy is equal to the internal energy plus P delta V. Now this P delta V is an interesting term. This is our work term. And so the P here, notice that it's P delta V, not delta P. Just saying the P for pressure means that we're dealing with constant pressure. And so when we do our chemical reactions in our lab, the pressure of the room is not changing, so we're doing things at constant pressure. So if there is work being done, then that work would have to be done by a change in the moles of the gas. And so I don't necessarily think about it this way. I rearrange the equation, but this is kind of what the book does. This is your book definition here. How I think about it would be looking at it from the internal energy. And then if we rearrange our equation, we get delta H minus P delta V. Now, a couple just terms and the way we think about the internal energy. The internal energy is really like a sum of a lot of different energies. This is your kinetic energy, your temperature, the potential energy that's involved in bonds, intermolecular forces, and a whole bunch of other different nuclear forces that we don't spend a lot of time in. But that's kind of the idea with internal energy. And again, our enthalpy is our change in energy or change in heat in our chemical reaction, and then this term is our work term. Now, one of the things that was thrown off initially looking at these things is, we're changing our sign here. How does all of this work? No pun intended. So if we consider like a syringe of gas, so I got my syringe, I got my plunger here, and then I've got all sorts of gas particles in here. So I have my gas particles here, and so then this is our initial volume, and then if I have if we have a decrease in the moles of gas, then to maintain or keep constant pressure, if I have a decrease in the moles of gas, then the volume must go down. And so again, decreasing the moles of gas in this case, in order to have constant pressure, the volume would have to change. What we have here is a negative change in the volume. The volume has gone down. If we take our negative delta V and plug it in here, then we get our new equation, we get delta E equals delta H minus a P times a negative delta V, and then delta E equals delta H plus P delta V. And so this is when, if we think about how this change would happen from a, going from a larger volume of a gas to a smaller volume, then the work must be, kind of going back to our sign convention, the work must be done by the surroundings onto the system, and that's where we get that positive work being done onto the system. So we don't spend a ton of time sort of like working with this equation very much, but some of the sign conventions and some of these ideas of work always kind of threw me off, so I thought I would sort of include some of these sign conventions. All right? Some ways that you could be asked questions about this. As an example, here's a very popular, very famous sort of equation. Nitrogen gas reacting with, nitrogen gas reacting with hydrogen gas, forming ammonia. Should be an arrow. There we go. So very famous chemical reaction here. And if we keep track of our moles of gas, we see that we have 4 moles of gas on the reactant side, 2 moles of gas on our product side. So what you could be asked, for instance, would be, is the internal energy equal to the enthalpy? So is delta E equal to delta H? And so this one way that you could be, that could be one way that one question you'd be asked. So again, if we have our equation of delta E equals delta H minus P delta V, we see that our change in moles, we have going from 4 moles of gas to 2 moles of gas. And so we do have a change in the moles here. And just like in our example, since we're going from 4 to 2, we have a negative change in the volume. So in a question like this, what you have is delta E equals delta H, again, minus P times a negative delta V. And then, again, this simplifies into delta E equals delta H plus P delta V. So in a case like this, since we do have work being done onto the system here, that must mean that the delta E is greater than delta H. Let me rewrite that. The delta E must be greater than delta H because we have this work term over here. And that could be one thing that you'd be asked. Again, we don't spend a whole lot of time thinking about that. There's a whole lot of other reactions and formulas that we spend a whole lot of time on, like summation equations, using Hess's law and bond energies. But they're all based on some of these ideas of the system and the surroundings and keeping track of the flow in and out of the system. Thanks.